Hello everyone and welcome back to the channel. In system design, we often think about services talking directly, like one API calling another. But what if you need one system to broadcast information to many others without knowing who is listening? What if you need truly decoupled asynchronous communication that can scale massively? This where the publish-subscribe messaging pattern shines. In system design interviews, discussing pub subsystems demonstrate a sophisticated understanding of building a scalable, resilient, and event-driven system. Today, we are diving into its core concepts and applications. Let's first understand the problem pub sub addresses. So, let's get our pen here. Let's say that we have server A or service A. Let's call it SA, and you know what, because we'll have too many S's. Let's say that we have service A, we have here B, C, and B. This is D, okay? So imagine a traditional point-to-point communication model, okay? Let's say that if service A needs to notify service B, okay, C and D about an event. For example, a new user has registered. A service A would need to know exactly. It will need to know about and directly calls the APIs of B and C and D. Okay, so it will send the request to each one of them. Okay. And if you add service E, if you have another one here again, you have to modify service A, and service A need to know the API call for service E and sends the request to it. So here we have a direct coupling. Service A handles all the requests to all the services. Also, we have a problem with sender scalability, because if service A might be bogged down waiting for responses from multiple receivers, especially if some of them are slow. Also, we have a reliability issue. If service B, for example, this one, is temporarily down, service A has to handle retries, which will add more complexity on service A. Also, we have fan-out inefficiency. Sending one message to many interested parties become complex and inefficient with direct calls. So these issues highlight the need for an intermediary system that can facilitate one-to-many decoupled communication. So what is a pub subsystem? Let's take the same example. A, we have B, C, and D. So at its core, publish-subscribe is an asynchronous messaging pattern when senders, which is A here, service A, knows, or senders knows as publishers, sends messages to logical categories called topics or channels. Receivers here, which will be B and C and D, known as subscribers, would register their interest in one or more topics to receive the messages. So we have here, this is our pub subsystem, okay. Our A service will send them the topic here, the message to this one, and all the services that are interested to this topic will pull the topic from it. The key concept here is decoupling. Publishers don't know who consumers are or who consumes their messages, and subscribers don't know who publishes them. Think of it like a newspaper or an audio or a radio station. The publisher broadcasts content, and anyone interested can subscribe or tune in without needing to directly contact the publisher. It's a fundamental shift from direct point-to-point communication to a broadcast models. Okay, so we need to understand this better. So if we want to understand this better, we will need to talk about four things. The publisher sends, the broker, which is stores and routes, the subscribers, which is the receiver, and the asynchronous processing. Let's talk first about the publishers, which will send. A publisher will generate a message, which is an event, and sends it to a specific topic on the message broker. The publisher's job is done once the message is successfully sent to the broker. Next, we have here the broker. Oh, sorry. In our example, the broker is this. This is the broker, okay? The message broker receives the message. Depending on the system, it might store the message for a period, for a period, or for example, for reliability and replayability, like Kafka, and then route it to all active subscribers of that topic. Next, we have the subscribers. In our example, B and C and D were subscribers or receivers. A subscriber, having previously registered its interest in that topic, will receive the message from the broker. Next, we have asynchronous processing. The subscriber then processes the message, performing its specific business logic based on the event. This processing happens asynchronously from the publisher. This intermediary role of the broker is what enables the true decoupling and reliability, acting as a buffer between publishers and subscribers. Okay, why pub subsystems matters in system design? First is for asynchronous communication. Publishers don't have to wait for subscribers to process messages. They send the message to the broker and can immediately move on, significantly improving the responsiveness and throughput of the publishing service. Number two, loose coupling. Services become truly independent. You can add new subscribers, change existing ones, or even remove without affecting the publisher. This makes your system much easier to develop, deploy, and maintain. Next, we have scalability. Publisher scaling. So publishers are never plugged by consumers. In subscriber scaling, you can easily add more subscribers to consume the same events efficiently, broadcasting a single event to many interested services. Consumer concurrency as well, like multiple instances of the same subscriber service can concurrently process message from a topic, scaling process power. Next, we have reliability and resilience. The broker acts as a buffer. If a subscriber is temporarily down, messages can be buffered by the broker and deliver once the subscriber comes back online. This prevents message loss. Lastly, event-driven architecture. A PubSub is the backbone for building reactive event-driven architectures, where services react to events as they happen across the system, enabling highly dynamic and responsive behaviors. Okay, let's talk about some challenges and considerations. So while it's a powerful, PubSub system introduces its own set of challenges. Number one, increased complexity. You are adding a new critical component, which is the message broker, to manage, monitor, and scale. Number two, eventual consistency. Data isn't immediately consistent across all services. Changes publishes to a topic will be processed by subscribers with some delay. Your system must be designed to handle this eventual consistency. Number three, debugging. Tracing end-to-end flow of message across multiple asynchronous services can be harder than debugging directly API calls. Next, message ordering. While some brokers like Kafka guarantee ordering within a single partition, global ordering across an entire topic might not be guaranteed by default, requiring careful design. Lastly, decouple messages. Brokers might deliver messages more than once. Subscribers must be idempotent, meaning they can safely process the same message multiple times without unintended side effects. So, How to discuss it in system design interviews. In system design interview, bring up pops up when asynchronous communication, loose coupling, or event-driven patterns are needed. Construct it with direct API calls. Discuss its benefits for scalability and reliability. And highlight the challenges like eventual consistency and the need for idempotent subscribers. Naming specific technologies like Kafka or RabbitMQ also shows practical knowledge. So that's it for this video, and see you in the future.